Assalamu alaikum. Uh, let's start lecture number 26, um, Mechanics of Solid 1 course, ME213. This lecture, we will discuss about the, how to draw shear force and bending moment diagram and using the relation among load, shear, and bending moment. And this method is also known as graphical method. Previously, in previous lecture, we discussed how to draw shear force and bending moment diagram using the equilibrium condition, so that sum of forces is equal to 0 and sum of moment is equal to 0. And in this lecture, we will look at another method that is known as graphical method by looking at the relationship between load, shear, and bending moment. Now, let's consider a beam, a simply supported beam uh, with the support at A and B units under distributed load W. And we want to find what is the relationship between this load W and internal shear force and bending moment. Now, now considering this small section C prime from the beam, and we making a free body diagram. So this is a free body diagram of that section. So there's an internal shear force at C. Now following the sign convention, so it will be positive upward, and moment clockwise direction will be positive. Whereas on C prime, so the shear force will be V plus delta V, because there's a distributed load, so the shear force is changing from C to C prime, so that change in shear force is delta V, and similarly the moment is also changing, so that we call it M plus delta M. Okay, now if we want to write the equilibrium condition for this section, so we can write over here Fi should be equal to 0, sum of forces in y direction is equal to 0, V, so V minus V plus delta V, so this force V plus delta V, and this force, the distributed force, we are converted into point load, that will become W delta X, considering a small portion that is a rectangle, so we can write as W delta X. So over here we write minus W delta X. Now if we look at this equation, now this V will cancel this one, and we only left with delta V is equal to minus W delta X. So minus sign over here, so minus WX will move over there, so this will become delta V is equal to minus W delta X. Now simply rearranging it, dividing both sides with delta X, and we can write for the section that dV by dx is equal to minus W. And if we simply write this term as dV is equal to minus W dx, and we integrate this, so that we have, if we integrate this term, we come up with this expression that if you talk about between point C and D, so we can write Vd minus Vc is equal to minus integral W dx. Now, if you look at this expression, that is nothing but area under the load curve. So it is nothing but area under this load curve. So what is the area of this load curve? And if I take the slope, so it will give me what will be the force distributed load at that particular location. Okay. Now we can also uh, have to take sum of moment should be equal to 0. So when we take relation now, if we take moment about c prime is equal to 0, so we can write m plus delta m. So we are taking moment on this location is equal to 0, so that become m plus delta m minus m, positive, clockwise we take negative, falling, and minus v times dx, this force. So this force, moment due to this force will be 0 because we are taking moment at c prime, and plus w delta x, that is the force, and this is the distance, and this must be equal to 0. Now this moment and this moment will cancel out. Okay. Now since we are taking a very small portion, so delta x square, so we can ignore that approaches to 0. So this term we can assume or ignore it, and we're taking it to 0. Now we left with uh, delta m is equal to v times delta x, and we can write into differential form, dm by dx is equal to v, or we can write this expression also as dm is equal to v times dx. And if we integrate it between again c and d points, so we have md minus mc is equal to integral v dx, and it is simply but area under the shear force curve. Now coming back to those expression, so if you remember that we have expression for the shear force, that was dv by dx, and that is equal to minus w. And if we are interested between point C and D, so VC minus VD, sorry, that will be VD minus VC, and that is minus XC XD W dx. Means if we consider shear force diagram, that shear force diagram is nothing but area under the area under W curve between C and D. So this is basically equal to the area under this curve, load curve, area under this load curve between section C and D. Now if I take slope at any location, it will give me what will be the value of load at that particular location. So this expression is basically showing me the slope of this curve, and that is load per unit length at that point. Now similarly, the other expression we have was dm by dx is equal to v, and the another equation we have md minus mc is equal to integral between c and d and v dx. So moment between d and c is nothing but area under this shear force curve. So what is the area under this shear force curve? And if I take a slope at any location, it will give me the shear force at that particular location. Means if I'm interested what is the shear force over here, so I can take the slope of this curve. So this is basically relationship between shear, load, shear, and bending moment, and we can use this to draw shear force and bending moment diagram. Now let's see a concept problem for this, how to draw shear force and bending moment diagram using this. Okay, let's see a concept application to draw shear force and bending moment diagram using the relationship or using the graphical method. Okay, Now we have a simply supported beam with a distributed load W, and we have to draw shear force and bending moment diagram. Now first we have to find the reaction at A and B, so that you can easily find by taking this beam as a rigid body and uh, putting the reaction over here, A and B, and you can easily find, and that will be equal to RA will be equal to RB, and that is equal to WL by 2. Okay. Now, in order to find the relationship between shear force and bending moment, okay, so let us take a section between A and B. Anyway, let's take a section over here, okay, and let's draw a free body diagram for that section. So if you draw a free body diagram for that section, so I'm taking that section over here and drawing the free body diagram. So this is my reaction at A, WL by 2, and we have a distributed load of W. So it's a uniformly distributed load. So let me draw over here W. And we have a shear force and bending moment, again following the sign convention. So we have a shear force and we have a bending moment over here. Okay. Now this distributed load we can change into concentrated load, and that is W into X. As you know that this distance we take as a X. Okay. Now we took a section, and let's take this section C over here. So we can write VC minus VA, and that will be equal to negative area under the load curve, and that will be equal to from 0 to X, because since this distance is X. Now if I write it so that we see at that location, I can write that will be equal to VA, putting the value of VA, that is simply WL by 2, and if I integrate it from 0 to X, so that will become minus WX, and this I can write as, if I take W common, so L by 2 minus X. Okay. Now if I want to find what will be that B, so VB, if I simply put X is equal to L, so VB will be simply minus WL by 2. So if I replace at VB, this X will become L, and this will be the value of shear force at B. Now, if you look at moment, if I look at moment, now, okay, now if you look at that VA, so we know that VA, that was equal to WL by 2, at VA that was equal to WL by 2. Now from WL by 2, it will be distributed in such a way that it will be 0 at between A and B, and it will be negative WL by 2 at B. Now, if we consider the bending moment, so I can write MC minus MA, and that will be equal to area under the shear force curve. Now if we want to write what is the value of V, so what is the value of shear force? So MA will be 0. Obviously there's a pin joint, so MC I can write, and we know the value of V from this expression. So putting this expression, we have W. Let's take common, so 0 to x, and that will be L by 2 minus x dx. Now if I integrate it, and the value of moment will be simply 1 by 2 W L minus Lx minus x square. Okay, now if you draw, and if you look at this expression, that is parabolic expression, so it will be 0 at A, so it will be 0 at A, and obviously it will be 0 at B, and it will be changing from 0 to maximum value, and it will come back from maximum to 0. Now what will be the maximum value? So if you remember that for the maximum value, the slope curve should be equal to 0. So this must be equal to 0, and we know that shear force will at that point will be equal to 0 for this loading. Now if you draw shear force for this problem, we have 1 by 2 WL, and it will be 0 at L by 2 and minus WL by 2, that is at B. Now if you remember the expression for V, so that expression was simply V is equal to W L by 2 minus X, and if you put X is equal to L by 2, so this will give us V is equal to 0, where we have maximum bending moment. And how we will find, if you look at the expression from the previous slide, so that expression for moment was 1 by 2 W Lx minus x square. Now if you put x is equal to L square, so and if we solve it, so that moment value will be 1 by 8 WL square. So this is how to draw shear force and bending moment diagram through the relationship between load, shear force and bending moment, and this method is also known as a graphical method. Okay, now let's see another example to further clarify the concept. So we have a beam. This is overhanging beam. We have to draw shear force and bending moment diagram for this overhanging beam. So we have support at A, we have support at A, we have support at B, and we have support, not support, we have load at B, that is 20 kilopound, 12 kilopound at C, and at support at D, and we have a distributed load at the overhanging part DE. Dimensions are given, so we have to find what will be the shear force and draw the shear force and bending moment diagram using that concept. Okay, first we have to find reaction at A and B. So taking entire beam as a free body diagram, so we have to determine reaction at A and D. Then we apply relation between shear and load to develop shear diagram, and then apply relation between bending moment and shear to develop bending moment diagram. Okay, now let's find the reaction at A and D. So if you take moment about A is equal to 0, about this point, so we can find what was the reaction at D, and sum of forces in vertical direction is equal to 0. So with that we can find what is the reaction at Y. Okay, now if you look at this loading, so from A to B, B to C, and C to D, there is no distributed load. So means the slope is 0, but it's a constant value. So if you look at the value from A to B, that will be equal to 18 kilopound. Means if I take a section over here and draw free body diagram, so that shear force will be equal to 18 kilopound. Similarly, from if I take a section at 1 as shown over here, and if I write the expression, so it will be equal to what? It will be equal to 18 minus 18 plus 20 and plus V is equal to 0. So that V will become at this location minus 2, and it will be constant between B and C. And similarly between C and D it will be constant, and that is equal to minus 14 kilopound. Because if I want to write over here, so that will become 20 plus 12 minus 18, and it will go other way, so that will become minus 14 kilopound. Now if I look at this distributed load from D to E, the shear force will be at D will be equal to area under this curve, under the load curve. So that is simply equal to 1.5 multiplied by 8. So that is equal to 12 kilo pound, and it will be obviously 0 at E. So this is the shear force diagram. So apply a relationship between shear and load to develop shear diagram. A zero slope between concentrated load and linear variation over the uniform load segment. Okay, now for the bending moment, that will be equal to area under this shear force curve. Now if you look at area under this curve or this segment, that is equal to 18 multiplied by this distance, and this distance was 6 feet. So 18 multiplied by 6, that is 108. So now the bending moment will be always one order higher. So it will start at 0, it will be 0 at A, and it will be changing linearly from A to this point B. So it will be linear, and the value will be at B will be 108 kilopound inch. Sorry, kilopound feet. So we are taking in the feet. Now, if you look at this, so area under this curve is minus 2 multiplied by 8, that is 16. Means the distance between, if you look at the problem, so at the distance between B and C is 8 feet. Okay, now if I want to write the expression for that, so that will be equal to what? 108 minus 14. So 108 minus 14, so that is equal to 92 kilopound feet. So at C, the value will be 92 kilopound feet. Now from C to D, it's the area under this shear force curve is minus 14 multiplied by this distance is 10 feet. So 140, so area under this curve is 140, so that will become 92 minus 140, and that is equal to minus 48. So at D it will be minus 48 kilopound feet, and it will be 0 at E. But if you look at this curve, and this curve will be parabolic. Okay, so bending moment at A and E is 0, and the bending moment variation between A, B, C, D is linear, whereas the bending moment variation between D and E is quadratic, because it will be always one order higher than the shear force. A net change in bending moment is equal to area under the shear segment. Okay? So net area will be net change in bending moment is equal to area under the shear distribution segment. Now, so And if you take a total of all bending moment, so bending moment change across the beam should be equal to 0 because it must be under static equilibrium condition. Okay, now, okay, let's summarize this section or topic. Uh, so using graphical method, we can draw shear force and bending moment diagram. But again, first we have to find the reaction using free body diagram, and for taking entire beam. Then we can apply these relationship to find shear force, and shear force between 2 points is nothing but area under the load curve. But if there is no load, then it will be constant. And similarly, the moment between 2 points is simply area under the shear curve. So reading assignment, please go through sample problem 5.4, 5.5, 5.6. Those are related to how to draw shear force and bending moment diagram using graphical method. Okay, now some important note regarding your maximum positive and negative bending moment where can occur on the beam. So that all depend on the type of beam support as well as the loading condition. For example, the maximum positive or negative bending moment can occur cross section where the shear force is 0. For example, if you look at this problem, that was a concept application we did earlier. That is our concept application number 5.3, concept application 5.3. So we draw shear force and bending moment diagram, and if you look at that, the maximum shear force is where the maximum bending moment is where the shear force is, internal shear force is 0. So if you look at the location, so where the shear force is 0, the bending moment is maximum. But if we look at the external load at that location, the external load is not 0. Now, the maximum positive and negative bending moment can also occur where you have concentrated couple or bending moment acting on the beam. For example, this one. This is your sample problem number 5.6. So if you look at that, concentrated bending couple is applied on the point B. Now if you see the shear force diagram, that is constant because both A and B, the shear force will be equal. The load is equal. But if you look at the bending moment, the bending moment is maximum at the point B where you have concentrated bending moment is occur. Now the maximum positive or negative bending moment can also occur where the concentrated load is applied and where shear force change sign. For example, this is again concept application number 5.1 that we discussed previous lecture. Now if you look at the simply supported beam with a concentrated load, if you look at the shear force diagram, so the load sign changes, the internal shear force signs change and where the load P is applied. Now it will be maximum bending moment will occur at that location as well. And the fourth point can be the point of support where the reaction force and where the shear force sign changes. For example, if you look at this overhanging beam, this is your sample problem number 5.1. So that related to previous lecture. Now if you look at this is overhanging beam and there's a load, there is a support at B where your sign is changing, so shear force sign is changing if you look at over here, and at B you have maximum bending moment. Now it can be positive, it can be negative depending on the loading condition. So these are the four important points when you're analyzing the beam. So the maximum positive or negative bending moment can occur depending on the loading condition and the type of support. So you have to be careful, or these are the general guidelines. And for the cantilever beam, just solve some problem. If you look at some sample problem as well related to cantilever beam, you will get the idea of those. So thank you very much and hope to see you for the next lecture, 27th lecture. In 27th lecture, we will solve few problems from the book, couple of problems from the book related to section 5.1 and 5.2. And these are the assignment problems, suggested assignment problem for you to solve. And the deadline for assignment problem for this section and the previous section 5.1 I will announce with this lecture number 27 and also deadline available on the CMS. So thank you very much and see you inshallah.